And then I can go really fast because then you can watch it again. Because I know whenever you have spare time, you're probably wondering, how can I watch Mark talk again? So I'm going to record it, then I'll post it.
Yeah.
It's recording. Yeah, I'm sure that comes up. You're all around the table. And all the kids are like, "Can we watch him again?" No. Okay, normative distribution and z-scores. We're getting into the world here of we're getting out of descriptive statistics and into some comparisons, and then we're going to start. There's the comparing of means for experimental design, and then ultimately predicting, which we're going to get into toward the end of the class. So there's another crash course on the normal distribution. I suggest she's a way better teacher than I am, and you just go in there and check that out. And fundamentally, the place that we're at is hypothesis testing. Now, that is, we have probably the best way to think about this is let's look at it from a treatment perspective. Okay, let's say they come out with. I'm gonna try and do this, and it's because there's actually no data for me to draw on here. But let's say they come out with a treatment for COVID. Now, this is not a psychology example. They come out with a vaccine, and so we have a current population that has COVID. No, these are active people who actively have COVID. This is a treatment. It's not a vaccine, so it's a treatment. And so we have this active sort of database that we have of the population of people who have COVID, and there's a certain number of people that die. Let's say 3%. So 3% of the population currently under current treatments dies. Now, we're continuing to develop new treatments because we want it to be less than 3%. And so we decide we're going to try out this new treatment. So we know the average number of deaths if we took a sample from the population as it stands, and that would be 3. We take a sample from that population and we give them the new treatment. And that sample has a 2.6% chance of dying. 2.6% of those people died. So we went from 3% to 2.6%. And what we want to find out is the degree to which that is a real change. Is it just by chance? Is it a significant enough change for us to change our protocol? It's to answer these questions as to whether or not this particular intervention was a good enough intervention. And we see here, I'm going to take this little, let me see if I can get my iPad here. This is a graphic. I have. Hold on. Okay, so you see here, I took this graphic out of the book and I put it on my iPad here. Now, let's change this to, that's the number 3, and this is the number, actually, let's change that to survival rate because it goes the wrong way, right? So there's a survival rate of 97%. And now there's a survival rate of 97.5%. 0.3. You following me on this? So this is our sample. This is the regular mean. This is the population mean already. We know 97% survival rate, 97.3 under the new treatment. So there's a difference there. There's a change. And we want to find out, is this change significant or not? So we develop a hypothesis and we say, when we're going in to test this, we can say, I think that this is a significant change. I think that our treatment did a better job than existing treatments in reducing the number of deaths, or in this case, increasing survival rates of COVID. And then whenever we're doing this hypothesis thing, we have a null hypothesis. There's always two hypotheses. There's the experimental hypothesis that says, this is what I think is going to happen. This is what I think we're going to see. There is a relationship. And the second one is nothing happened. There's no relationship. There's no effect. And that's called the null hypothesis. And I think it's really important to recognize there's a philosophy associated with this. It's very, very critical. And that is, in the world of science, we go into answering questions saying, unless you can prove it, there's nothing going on. There's the null hypothesis is the assumption. I'm going in, there's no relationship here unless I find evidence that there is. And that itself, that perspective explains some of what we see in terms of, like I was talking at the beginning of class about how individuals in the public don't really understand the process of science, that it goes in. And so every time there's a new evidence, it's changing the bar. It's changing those assumptions that we go into. And it's almost like a skeptical point of view. Like, things are the way they are unless you can prove otherwise. Unless you can give me data, I'm sticking right where I am. And that's that's the philosophy of these two hypotheses. So if you ever do a study, let's say we're talking to, we're going to be in the jail with Jordan, and Jordan is thinking about implementing a program on literacy, and she implements that program with a sample of her jail population. Her null hypothesis, her assumption, almost going in, is that it's not going to make a difference. Until you can find absolute evidence, then there is no relationship. Now, this is where it gets a little sometimes difficult to understand about the standard bell-shaped curve. And I'm going to try the best I can to teach this. Now, the bell-shaped curve, the normal distribution, what the book refers to as a normal distribution, and I have said this before, and I said I was going to come back to it, is not necessarily a distribution of scores when we get to, it's a distribution of the means of samples. So what that means is we take anything in the world, let's say in this case right here, we're looking at final exam. We'd look at final exam scores, and there's millions of them. Let's say there's millions of people that have taken this final exam, and we're sampling groups of 100. And what you'll get is over here on 65, there's going to be this amount. There's going to be that amount right there of samples that are going to have a mean of 65. There's going to be that number right there that have a mean of 85. Most of them, however, are going to be right in the middle and have a mean of 75. And that's where we see that mu, that letter right there, that's the mean of the population. So when you're looking at a normal distribution, you're looking at the whole population, and I'm sample, 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 and the thing I'm graphing is the mean of each one of those samples. And science has repeatedly demonstrated in the actual practice of doing this that if you graph it, it approaches this perfect natural curve. Okay. Now, what this then means is, given no intervention, let's go back to our, what was it, 97 and 97.3. If I was going to, if this are the true data, that 97.3 was way over there, if I'm just going to go in and I'm going to sample 100 people who have had COVID and their mortality rates, there's a really good likelihood that I'm going to get somewhere in here. In fact, there's a probability likelihood that I'm going to get one in there, just randomly pull them out. Something out here is pretty rare. It's pretty unlikely that just by chance, I'm going to go out, grab a sample of 100 people, and they're going to have a 100% success rate or survival rate. Pretty rare. And probably pretty rare that I'm going to grab a sample and they're going to have a 50% survival rate. Those are incredibly rare instances for sampling. So the logic of this is, if my number, my 97.3, is so different that it pushes me out here, and the chance of me getting that by, the probability of me just picking that is really low, then it's probably because of the treatment and not because of the sampling. Do you get that? So the only thing that would have pushed it over there would have been the treatment, because the likelihood of me getting 97.3 as a number is really unlikely. And that percentage point, that degree to which it's unlikely that this occurred by chance, so therefore it must be because of your intervention, is the decision point that we make for our hypotheses. And what it makes us do, and this is the language that you will see in the literature, you'll say, the evidence points to my results as being significant with a probability. Let me get a little blank sheet here. So you see, my results are significant. And then you're gonna see things like P is less than 0.01. And that means that the probability that my sample was by chance is less than 1%. And the way that looks on the graph is, without any interventions, that my particular results would have been somewhere over here. And the likelihood of getting that by chance is really low, so it must be because of my intervention. You might still be wrong, but the chances that you're wrong are less than 1%. That's pretty good. And the other one you'll see is, P is less than 0.05, which is 5%. That's a little bit more loose. I mean, I have a little bit more wiggle room, but 5% chance, or because I use chance and probability here, but if the probability of this happening naturally is less than 5%, then we consider it a significant result. We have something to say. If it's not less than 5%, if there's a 10% chance that this came out, that this could happen by chance, that's not good enough. That doesn't meet the scientific criteria of let's go with it. We've discovered something. We have a new treatment. And you could probably imagine part of what we're looking at with the efforts to create treatments and responses to COVID is the fact that many of the studies are showing positive results, but they're not significant. They could happen by chance. So the president's drug of choice, which he didn't take, by the way, when he got COVID himself, I can't remember the pronouncing of it. Yes, there are case studies that have been done, and there have been some studies that have done that have shown an effect, but the effect was not so great, was not so different that it couldn't have just happened by chance. So therefore, it doesn't meet the criteria of science, and therefore we have this argument between something that might work and then something that will work, and it's all based on this statistic. And that's where the science thinking comes in, because the science is not going to say, yeah, and then science is going to come in, they're going to say, we're not going to recommend this until we're pretty damn sure that the sampling didn't just get a bunch of weird people that were way out, that were likely to get healed anyway. And so this also delays the process of getting drugs out to the market, because they're still looking for that gold standard of reliability and in this case significance. So we're in that world right now. We're in the world of saying, essentially, is the reading program that Jordan puts into the jail, is it really working? Is it really making a difference? Because it's a lot of work. And so if you were the person working in the jail and you put this program in and it's occupying your day and you have to prepare for classes and you're grading all kinds of stuff, and at the end of the day it doesn't make a difference, stop doing it. Because it's not making a difference, and it's not. And if you're going to use the criteria of science, it has to make a lot of difference. Now that doesn't mean that, and in truth, the reality of this, the gap that exists in science is it could be that when Jordan put that program in place, that it actually was the magic for like 17 people. It was the very thing that they needed to do. It was great and it was awesome. And you still came to the conclusion and you shut it down. It doesn't mean that it doesn't work at all. It's that it doesn't meet the criteria for us to call it a scientific discovery. You may choose to then customize. I mean, this is why treatment is customized all the time. There's probably some people that responded very well to that drug, and good. I'm glad, maybe for some people they're going to give it a try. It becomes one of the drugs of choice, but science is going to sit there and say, hey, let's make this the standard treatment, because it didn't cut the cake. It didn't do it. And so we're going to be, this is what kind of chapter 7 is about. And so let's continue a little bit along chapter 7. I hope we got that pretty clear here. So we see that, if our sample would be pretty rare to occur by chance, then we're doing okay. Now, the way that we know that our sample, where it lies upon look how far it is from that population mean is through by changing that value into a z-score, which we've already done. So it goes into z transformation here about how we change these z-scores into units of standard deviation. And I think what I want to show you is this figure right here. And let's put that up on the bigger screen here. So here we have, this is the portion of sample means that you will find in these areas by standard deviation. So right here you see there's the average right there, mu, like mu. 1 standard deviation, 2 standard deviations above. Remember, that's variance. That's a degree of variance here. Between -1 and +1 is 68%. Then there's another 13.6% here. So let's put that down. 26, 27.2. (95.2%) between 2 standard deviations. That's 95. That means if you're sampling something, there's a 95.2% chance that your mean is going to be between 2 standard deviations. So you're really looking at this 2.2%. Everything above 2 standard deviations is really rare. Is really, really rare. And so when we change our scores into z-scores, it gives us an exact point along here, along this continuum here. It gives us an exact score in standard deviation units, and we can then refer to we're going to refer to a table in our book to determine how unlikely it is. What is the exact percent? These are very broad. We can get the exact percentage of a score with exact likelihood that that would come out. So our particular group has a mean of this, and we say, what compared to the population, how rare is this that we would get this by chance? And that brings us back to when we look at these, when we're taking a score and we're changing it. Oh, I'm sorry, I was looking, I thought I had the book up again. When we're taking a score and we change it to a z-score, we can look up that z-score on the unit norm table. Okay. So in SPSS, we can take a score and we can convert them to z-scores. And there's a formula in the next chapter where we actually go into how to calculate that. And then, do you have your books with you?
Yeah, I just need to grab mine real quick.
Yep. Okay, I want you to look on page 347. In the textbook, one, not the lab manual. And what you're going to see a table, and it's multi-pages long. You just turn the pages, you can see it just keeps right on going. Another 2 pages. And in the blue column is the z-score itself. In the white columns is the percentage of scores that would be between that score and the mean, and the percentage of that and then the next column, the tail, would be the percentage of scores that are above that score. So if I had, now remember, these are in units, z-scores are units of standard deviation. So when you compute your standard deviation, there you go. You have that unit that you can then see, well, where's my score? How many of those units does it go up? And then calculate and get that z-score, which is your score in measured in standard deviation units. So on page 347, now just so both of you know how to read this, when you look at a decimal, I'll do the first one. At the top of the 4th blue column on that first page, there's a z-score of 0.66. If you have a score from your results that has a corresponding z-score of 0.66, that means it's higher than 74%, and it's lower than 25.46%. You follow me on that? That's where that score lies. These are percentiles. Compared to the rest of the distribution, if my z-score for my score was 0.66, then 74.54% of the scores will be found below that score. 25.46% of the scores would be found above that score. Okay, Jaden, down from that column, look at 0.73 and tell me what percentage are below and what percentage are above.
So you said 0.73, right?
Yep, 0.73.
So it'd be, are we rounding it or no?
Just do the full decimal.
Okay, 0.7673, which is a percent, right?
Yeah, to do it a percent, you move the decimals over. So you do 76.73%.
Okay, it would be below, and 23.27 would be above.
You got it. Now, Jaden, turn the page. And on page 348, I'm sorry, Jordan, on the top, on page 348, the 3rd blue column over is 1.65. So this is 1.65 standard deviations. What percentage?
So it's 95.
Yep.
Oh, sorry. 95.05% is below, and then 4%, 4.95.
You got it.
Wouldn't that be?
You got 4.9%. Now, the reason why I picked this one, Jordan, is when I told you about significance and we were looking at for the 5% and we're looking at the 1%, what's important about this number right here?
It's below 5.
It's below 5%.
I mean, above. Yeah.
Yeah, the scores that are above less than 5% or above. So 1.65 z-score is the critical level in every study in the world. If your z-score, if your mean from your group or your score is 1.65, the z-score is 1.65, then it meets the 0.5 or 5.05, sorry, it meets the 5% criteria. Jaden, what z-score do I need to meet the 1%? If you look at this, you're going to be looking for a tail score that's less than 0.01.
Do you want like where it starts?
I want the z-score in the blue column that goes along with it.
2.06.
Say 2.06. Nope. It has to be less than 0.01. 0.0197 is more than 0.01.
Oh, so I want to keep going.
Yep, keep going till you get less than 0.01. It's a little tricky to get used to this.
So 2.33.
You got it. That's it. That's the one. And if you look, 99% is below. This is the 1%. This is, every time you hear that number, this is the 1%, meaning individuals, let's say we were talking about money, people who make 2.33 standard deviations above the average income are in the 1%. Right there. That's what that means. People who score 2.33 standard deviations above the norm in an intelligence test are geniuses. They actually, we have words to describe this 1% level. So that 2.33, so we have our raw score and we want to see how rare it is. We convert it to a z-score and we look it up and we find out where that particular score is in the big picture of that whole distribution. So excellent work. That's how you use this table. You're going to compute a z-score and then you're going to look it up here and you're going to make a decision. Is it significant or not? Is it, because if, let's say let's say your score was 1.38, there's a 8.38% chance, that's right where that is. There's an 8.38% chance that you got that by chance. That doesn't cut it. It's still pretty rare. Now you could get, if you got an SAT score of 1 and it converted to a z-score of 1.4, the z-score is 1.4. Jordan, how many people did you do better than? What percentage of people who took that test did you do better than if you got a 1.4 z-score?
Would it be the 85?
For 1 point, the blue box would say 1.4. How many people did you score better than?
Well, mine's, I don't know if it would be the body or the tail.
It would be the body.
What do you, mine, I don't know if I'm looking at the right one. It's 85.08%.
I don't
Am I
know.
the wrong one?
I don't know what you're looking at.
1.0. It's 1.04.
1.4. not 1.04. Sorry,
Oh.
1.4.
Where's that?
1.40. It's like the next column over in the blue.
Oh, okay, gotcha. So 91.92, that one?
You scored better than 91.92% of the population. Did you do well? If you
Yes.
scored better than 90% of the people, did you do okay?
You did.
Yeah,
Did all right.
yeah, you still did okay, even though it's not genius. We know you're a genius, but it's still good. So we use these scores for cutoffs. So let's say there's a, and I think I might have mentioned this too, now that we have the table in front of us. Sometimes admissions departments for colleges or programs or whatever are going to say, well, you need to have a score of this level or you can't come into the program, and they say SATs, we want the top 10%. You have to be in the top 10% of people scoring. So your Z-score, according to this, it has to be anything that's above in the 90s, right? So anything like 1.29 and above, then you're in the top 10%. So those numbers in the white columns, the body and the tail, they are percentages. Think of it like change in a dollar. It's like 95 cents, 0.5 cents. You know, just, so if you want to change it to percentages, you move the decimal point to the right 2 spaces, and then you can talk about percentages. And so when we say, and those would be the P levels, the P is the probability. And when we're reporting this out, we'd say, here's my results. They were significant. And the P level was less than this amount. And depending on the actual reporting, depending on the format of APA, some people will simply say it was less than 0.05 or it was less than 0.01 and they're good. But sometimes people will actually report the number and they'll say P is equal to 0.0024. They might actually put the actual number. And then we're like, oh, that was extremely significant. Not just less than 0.01, it was like a lot less than 0.01. And so you can see that giving out that stuff to the reader. Okay, that pretty much brings us to our 2 labs for homework for chapter 7, which is 23 and 24. So I want to kind of go over these a little bit. If you can open up your lab manual. To lab 23, this is the normal distribution. So number 1, there's 2 questions. The percentage of the area under the curve between the mean and the rightmost end of the curve. That's from the middle all the way to the right. What the heck, right? Take some notes on this. Let's answer some of these questions. Jordan, what do you think the answer to that question is? From the mean all the way to the right.
50?
Got it.
Is that wrong?
Yeah, that's it.
Oh, I was like, okay, good.
Half. Everything's half is above the mean, right? So Jaden, what about the percentage of the area under the curve within 1 standard deviation of the mean? Just one of them. That's from the mean to 1 standard deviation over. What percentage is that? And there's actually there's a table in the textbook. Well, I showed it, I had it on my iPad too.
Are there only there's only two standard deviations from the mean, right?
I'm sorry, say that again?
Like, so if you have the mean in the middle, there's two standard deviations and we're only going one.
Well, it's asking for one standard deviation, like you're in the middle and one standard deviation over. Either
25.
way, either way. What percentage is underneath there?
Would it be 25?
Nope.
I don't know.
Look on page,
Is it 95?
nope,
Oh,
look on page 148 of your textbook.
oh.
What percentage is from the mean to one standard deviation? What's in there? Jaden,
The
Who do you?
34.
Oh, okay.
34%, right? What percentage? Okay, that's the answer. That's the answer to B. There we go. Let's have fun with this. What percentage? Okay, Jordan, I want you to do this one. What percentage of scores happen between +1 standard deviation and +2 standard deviation and -1 and -2 standard deviations?
I know this. Would it be 96?
Nope.
Am I way off?
Yep.
Would it just wait? Would I just add the two? I don't know.
Look at one between one standard deviation and +1 standard deviation and +2 standard deviation. How much is in there? This is on the graph on page 148.
Yeah. Is it 57.6?
So 13.6, right?
Yeah.
And how much is in between -1 and -2?
Oh, I don't know. I'm confused.
On the other side of the graph.
Yeah, I got nothing. I don't understand.
Okay, I'm gonna put the graph up on the.
Yeah.
Did you say between the -1 and -2?
-1 and -2.
And +1 and +2?
I'm making that one up. That's not part of the lab. Okay, you see this right here?
Yep.
So the question that I asked Jordan, I'm sorry, the question that I asked Jaden, geez, one of these days,
No.
I asked how many scores went from here to here? And the answer is 34%. Jaden, I asked you, how many scores exist between one standard deviation and two standard deviation and -1 and -2? So there's 13.6 over here, 13.6 over here, 27.2. You get that?
Oh, yep.
It's all these people and all these people. You'll never get asked that question, ever. But I ask it. So you can get some real flexibility with this. So Jaden, How
Yeah.
many people, what percentage of the population is above +1 standard deviation?
15.8.
You got it. So it'd be these two, right? That's everybody above. And of course, the same would be down here. So these are these first questions in the we're back into lab 23, normal distributions. And we're done with question 1. Using the unit norm table. Let's go ahead and open that up. And let's do the first one on this. Using the unit norm table. Find the probabilities that correspond to the following z-scores. And what you want to report out is the tail. You want to report out the tail. And there's a tricky one here. So Jordan, 2.0. What's the tail on 2.0?
It is 2.28%.
You got it. Because it's asking for probability. So you have to report that in percent, meaning there's a 2.28% chance. Jaden, what about 0.5?
Um, 30.85%.
You got it. Now, we're going to stop here because I'm just going to tell you when you see a negative number, the next one's is negative 0.75. Just look up the positive. But in this case, you're still reporting the tail, but understand that's below, right? It's going the other direction. Just you have to keep that in mind. But when you use the table is just the positive side, but you would just look up 0.7 and you would say, well, this is at this z-score, this is the number of scores below, that percentage below. So make sure you make that distinction when you're talking about negative scores. Now, B is just the reverse. You're looking up the tail. So, all right. And in number 3, is going to involve some very basic math. And that is the SAT, the mean is 500. So let's use this little graph that I have right here. Let's say the mean is 500. And each standard deviation is 100. So this is 600, 700, 800, 400, 300, 200. Okay. That's what you get from the instructions. You get that the mean is 500. One standard deviation above that would be 600. Another standard deviation would be 700 and so forth. So what is the probability of having an SAT score of 130? That's way down there. In fact, what you're going to find Actually, this just occurred to me when we did this lab last time. What you're going to find is these scores are incredibly low. Like if you think of an average of 500, I mean, look at those numbers, 130, 120. They're more than 3 standard deviations below the mean. These people flunked the SAT. They did really, really, really bad. So you're going to find the answers are going to be extreme, like 0.0003 or something like that. So just I think that they might have meant to put higher numbers there. And I think I'll make a note to myself to make sure that I change those for the future labs. Now, the point is you have to figure out if you have a score of 130, then what is that in terms of standard deviation units? What is that in terms of z-scores? And so that's what you would then convert. And you can do that with some math. In fact, see that equation right there? That's the equation for a z-score. So let's say let's take 420. Let's say my number was right here. I'll put a little red mark on it here. There's my score, my 420. What's that? What's that in terms of z-score? Should be 420 minus 500 divided by 100. So that's minus 80 divided by 100.
Why is it 100?
That's the standard deviation.
Okay.
Yeah, this is the population mean. It's the population standard deviation. So 420 minus 500 over 100 minus 80 over 100. That's going to give you it's going to give you a minus, but then you can look up the z-score based on the positive of that. What's minus 80 over 100?
So that's what we would do. That's what we would do for these questions.
Yeah.
Like use that equation.
Yeah, look at like 130.
Okay.
Say so 130 minus 500 divided by 100. I'm just giving you the formula that's actually in the next chapter. Again, there's some really weird ways that they organize information in this book that I think they could have put this particular equation earlier. But you can just do the math.
Once you find the answer, and you look at the table, are you looking for the z-score?
Yep.
Okay.
Like the answer to that equation is the z-score. You look up that z-score and then you report out. But like I said, these right here, they're incredibly low scores. I think that was an error in the lab manual that they gave, 130, 120, and 91. I mean, come on. The average is 500. These are really bad. Like those are, like for the first 3. Now the next one is different. When you go from 350 to 650, you're looking at a change. You have to do some math. I'm going to leave that to you. You can do this in the next questions. And 24, lab 24 is the same thing. It's more of the same thing. You're given the mean and standard deviation of both the ACT and the SAT, and you're comparing them. The mean and so those are populations. The population, if you look on lab 24, the ACT has a population mean of 21 with a standard deviation of 3. And the SAT, just like we had just done, has a mean of 500 and a standard deviation of 100, and then has you look at individual scores compared to those standard scores. And I think I had done this as an example when I first brought up z-scores. I used ACT test and SAT test, and like one is, they're based on different, like comparing different numbers. If you convert both of them to z-scores, we can compare them as to what they mean in the big picture. Okay. Now in the, remember this is being recorded too, so you can watch this confusion again. There's a discussion where I'm having you go up and look up an article in EBSCO that uses z-scores, just to see how they're being reported out in the literature. So you get an example of that, and then it goes right into the labs, and we're into chapter 8. Cool. All right, so chapter 8, if we're ready to go on that.
Is chapter 8 due this week too?
I'm sorry?
We're doing chapter 8 as well this
Yes.
week?
Yep.
Okay, I just
We had
wasn't
that
sure.
rough start at the beginning, and we're going to have to double up a couple times. And just because I'm thinking about it now and I might forget it later, is schools close next Wednesday. So I'm going to be doing recordings for next week's stuff. And so I will post those, and you'll have those to go with for next time. Okay, hypothesis testing logic. I used this phrase already today. This is kind of, again, you get this sort of like weirdness of the way they organize the information here. We're back into hypothesis testing. I talked about that a little bit before. And here's that formula. An odd place for it, but so here's the z equals x minus the population mean divided by the standard deviation. Now the little brain bomb that's going along here is kind of get your head wrapped around this concept. It's really not, it's not important to learn it solid right now, but just to kind of let it sit in the back of your brain and you know, ferment a little bit. The larger your sample, the more it represents the entire population. The closer it is going to go to the real population. The population, sometimes we don't know. The standard tests that we've been doing, the SATs and the ACTs, we do know the population scores, but oftentimes we don't know the population score. So we have to take into account that we're doing a sample. So you'll look when we're converting the, when we're using z-scores, and we do know those areas, but we want to take into account our sample size, you'll see the next equation reduces the built-in variance of our z-score, and therefore makes our z-score higher. If the denominator goes down, the more we divide the standard deviation by the square root of the n, the smaller that number gets. The smaller the denominator in a fraction gets, the larger the z-score is. This is the mathematical reason why really, really big samples produce high z-scores all the time. They produce significant results all the time. we're going to get into at the end of this chapter, but more later and a lot more next semester, we're going to get into effect size. Sorry, I had to get a recall the effect size, meaning effect size is the degree to which your intervention actually made a difference. Because if you do a really, really big study, you're going to find significant results. But what if that significant result is simply because of this high N, but the actual change, the average change is really small? It might not be worth it. So let's say we have a new treatment that comes out for COVID, but the study involves millions of people. An incremental change will come out to be significant because the Z-score will mathematically be really high. But what if the change is only minute, like it went from 3% to 2.98%? Might not be a big enough change. Like, yeah, it was significant because we had 1 million people in our sample, but it's not a big enough change for us to say, okay, let's implement this across the board and spend millions of dollars on it. But there's your Z-score formula that you're already using. And I want to go into this section right here, the logic of hypothesis testing. And this is a little bit of reframing of what I've already said when I talked about creating hypotheses. You look at the steps here in the research method process. You've done a bunch of research. So Jaden, you're working with kids. You have done some research and you have found that kids, when they are doing seat work on their, at the table, they're doing worksheets. I'm not sure if you still do that kind of stuff, but you're doing worksheets, they're filling all out, and you find out that you read somewhere that if you print those on blue paper, students do better. Okay, so you're going to try it out. So you have a research question, and your research question is, do students who take their seat work and do worksheets printed on blue paper perform better than those who are doing it on white paper? I wonder, curious minds want to know. So your hypothesis, your experimental hypothesis, you'd say, well, based on my reading, I think it's going to do it. So I'm going to say yes, quote, students who complete worksheets printed on blue paper will perform better than individuals who on white paper. Your null hypothesis will be there will be no difference between the scores of students who did their work on blue paper versus the students who did their work on white paper. You have the two groups, they're going at it. You collect the data, you compare it. You're actually into t-tests now. This is another set of tests when you're looking at two groups like that. You calculate your statistics and then you find out, okay, did they do significantly better, or did it really not make a difference? And blue paper is a little bit more expensive, so it's not worth it for the little difference that we're going to make. And that's how science moves forward in terms of, now we're still into Z-scores and whatnot. So we're going to be kind of comparing on, standard scores. So let's just say you're going to take the SAT and you're going to do the SAT on blue paper or white paper and see if that's going to make a difference. And then you can look up the Z-scores and you can find out whether or not there was a significant difference in those. So here's through the steps. There's the scientific and alternative hypothesis. Look at the way that the null hypothesis is the standard and the alternative hypothesis is the experimental one. Again, that thinking that says we first believe there's no relationship. First, we're skeptical. Blue paper doesn't make a difference. Nope. I don't care what everybody said. It doesn't make a difference. When it comes to hypothesis testing, I'm going to say the null hypothesis, there's no relationship between the color of the paper and how well they perform. However, I'm a scientist and I'm going to explore. So my other hypothesis, my alternative hypothesis, is that there is a difference, that it actually increases scores. Now, in this next part, it says two-tailed or one-tailed. Depends how you ask that question. So it's totally up to you. And let me explain. There's two ways I could answer that question. If I say, my hypothesis is students who do their SATs on blue paper will perform better than on white paper. That is what I would call a one-tailed test. I'm not interested, the way that's written, I'm only interested in one direction of change. It's either going to increase it or it's nothing. I might ask a different question and say, students who take their SATs on blue paper are going to score differently than students who take their tests on white paper. That means it could improve it, but it could also decrease scores. And that's a two-tailed test. So I'm open in the second way that I asked that question, I'm open to the blue paper being bad and it makes people do poorly. Whereas in the first one, I'm only concerned if it makes people improve. Now it would make sense for us to be always open to the other, right? It's always open to that. But it changes how good our statistics need to be, because if I'm doing a one-tailed test, if I'm just looking for one direction of change, I'm just looking to see if blue paper increases scores on the SATs, then my level of confidence of 5% or 1% is going to be in that one direction. My score has to be better than 95% or 99%. On a two-tailed test, the 5% level gets divided between both sides. So if I'm going to say it affects it either way, then I'm opening myself up to a higher degree of expectation to prove my point, because let's say 5% is what I've set my criteria at. I want the scores to be high enough that it's, less than 5%. If I'm a two-tailed test, it's actually less than 2.5%. So that's harder to achieve. So a lot of studies, because they're trying to produce, this is part of the politics of psychology. It's pretty hard to get a paper published that doesn't have significant results. So psychologists over the years have developed a habit of shooting for numbers that will give them something to publish. And so they'll pick those one-tailed tests to go and so they only have to be better than 5% rather than 2.5%. And so you see that little difference there. Now, again, let's bring up the testing that's going on currently with vaccines and treatments. Jordan, when you're testing medications, do you use a two-tailed test or do you do a one-tailed test?
Two.
Why?
Because it could make it worse or make it better.
Another reason why medications don't come out quickly is because the criteria is not only very high, but it's split always. Medications and treatments are always split on a two-tailed test because, and this is a term for you, it's called iatrogenic effect. The iatrogenic effect is the negative aspect of any treatment. It's the side effects for some people. So is the treatment causing more problems than it's solving? So whenever we're looking at treatments, we're always looking at that. Does it give a positive, but what are the negatives? And that makes, so if we're looking for significant results, it's actually raising the bar again in that way. And again, that's why we're seeing a delay. Well, not that we're seeing a unique delay, there's always a delay when it comes to treatments and whatnot. Okay, so that's creating a hypothesis, the null hypothesis and the alternative hypothesis. The null hypothesis meaning there's no relationship at all, and the alternative or scientific hypothesis is the one where you write it to being one-tailed or two-tailed. And it's totally up to you. There's no standard on that. You can do whatever's appropriate. The next step is you actually set that decision level. That am I going to look for 5% or am I going to look for 1%? Do I really, how far do I want this to go? And that, of course, depends on the criticalness of what you're trying to do. These are judgments that come along. Now, I'm going to tell you, I have met many, many, many researchers who have studied who never did this. They waited until they got their results. And then, because if you don't get good results, no one's going to see it anyway. But the notion is that we kind of like, okay, I'm shooting, this is not that critical that I really, really need to be sure, like in medications or treatments or, investments or something like that. I don't really, really need to know. So I'm going to go for 5%. It's a little bit more loose, gives me, but if it's critical, I don't want to make a mistake. We go to the 1%. And then we calculate our data. I'm just making our way through here, and then calculate our statistic. And really all we're doing, and if I can kind of summarize everything we've talked about, is, again, we're talking about Z-scores right now. So we're looking at standard scores that we all already know. So let's go back to the jail, and we have a standardized reading comprehension test that we're giving to the prisoners as they enter into this program. Okay, so we're going to be able to compare their reading to standardized scores. And all we're saying is, I'm going to try something. The null hypothesis is that it doesn't make a difference. The experimental one is that it does make a difference. And in this case, I'm hoping it's positive. So I'm going to go with a one-tailed test. And I'm going to test them. I'm going to put a group of them through this program, and I'm going to test them on this standardized test. And if they are if they're far enough above the mean that it's less than 5% chance that I would have got this naturally, then the program made a difference. That's it. That's everything. That's the kind of the pragmatic way. I mean, it obviously gets way more complicated when we look at other research designs, but essentially you're looking at the numbers telling me that this is making a difference. Now, I'm going to tell you, as you venture out into your fields, that this kind of practice, what I mean by that is that interventions that are done in schools and in jails and whatnot are rarely, very rarely put to that test. So Jaden, I'm going to ask you, you work in a school and you see teachers doing innovative stuff all the time. I hope they're trying different methods. Have you ever seen somebody do a comparative analysis between a group that got it and a group that didn't get it?
Yeah, since like virtual learning, we have 2 different groups come on 2 different days, so I can assume
that you do see them.
Yeah.
So there's some groups that get it and some that don't.
Like understand everything's, yeah.
I'm sorry?
Like 2 groups that do and don't what?
Okay. Yeah. And then you can compare that to something like a standard score or something like that to see how well it went. So there you go.
Um,
Yeah. That's pretty cool. That's pretty cool. So so that's kind of the point of chapter 8, is to kind of get into that sense that we are forming hypotheses, gathering data, and at this point, we're comparing them to standard scores where we know the mean and standard deviation of the population. So we're looking at standardized testing. We're looking at populations that we already understand, already big data that we already have out there, and we're comparing to that. We're in the following chapters, we're going to be starting to get into what are called T-scores. And that's when we don't know the population, but we might compare two groups, or we might take one group and test them before and then test them after, and we see if there's a significant change in there. You're looking at that kind of testing, which is sometimes even more likely to happen in schools and prisons rather than looking at standardized tests. You know, you're looking at two groups. Like, we did this health science seminar in this group. We just did the regular health education in this group. Who performed better? And we make a decision as to whether we want to include that health seminar and that is done with a different test because we're comparing groups, and that's the t-test that's going to come up next week. Okay, so that brings us to labs 25 and 27. And in lab 27, you're only doing question 1. I'll take a quick gander at this, see if there's anything that strikes me as something I didn't explain well. Oh, in 25, I'm going to go back here a little bit. In 25, they go a little bit into error. And there are two types of errors, and this kind of it gets put in here. It's really taken care of mathematically, and with everything that we're doing up till right now has acted by setting high criteria, by having good design, by using standardized scores. Those are all ways that we reduce error. That we're not doing, you know, we're not getting, you know, flippant results. But we do categorize them mathematically into two types of errors. And type 1 error is when we reject the null hypothesis and we go with the experimental hypothesis, when in fact, it's not true. This is called a false positive. Type 2 errors is when we reject the null hypothesis when it's false. It's failure to reject the null hypothesis when it's actually true. So let me throw it to you this way. My wife is the infection control person at Cedar Ridge Long-Term Care. So she's in charge of all their COVID protocols and all of the testing and whatnot. So I'm up to my neck in COVID information here. And there's two types of tests that they have. Have either one of you been tested for COVID? No. Have you ever been tested for the flu? Take that long Q-tip and it feels like they're getting a brain sample. They go all the way to the back of your, okay? Well, there's two types of tests. One of them is that one. Big old long Q-tip, right to the back of your nasal cavity, sample, stick it in a tube, and they send it down to the state of Maine CDC processing lab. The other one is at the point, it's called a POC test, point of care. They have the machine right there. And they take a smaller Q-tip and they only go a little bit in one nasal and they swirl it around, and they go in the other nostril and get swirled around. Basically, I call them booger samples. And they put it in the machine, and it does the test right there. Now they operate on different principles. One has to do with the actual detection of the virus, and one has to do with the detection of certain proteins associated with the virus. Now, the point of care test has a 3 to 5% false positive rate, meaning type 1 error. It's going to say you have it and you don't. The one that they send down to the state has less than 1%. It's like a minuscule amount. It's an incredibly accurate test as long as it's done appropriately with saline and all that stuff. Procedurally, it's an incredibly accurate test. So they use the tests in conjunction with each other. One is more convenient. If I need to test someone right now, I'm test them right here. If it's false, that's probably okay. There's not a whole lot of evidence for type 2 errors giving false positives. I mean, false, like you have it, but it says you don't. There's not a whole lot of data to suggest that it's full of type 2 errors. However, if it's positive, I know right now I can take action, but I'm not going to end it. I'm going to take the other test and I'm going to send it down, and they both have to be positive in order for someone to have a confirmed positive outbreak. So that's one of the challenges that goes on with that kind of testing. The same thing happens when we're here. We might do our study, we do our statistics, and we find out that we're saying, yep, I got significant results, it's working, this is great, blah, blah, blah. And nope, there was an error. We actually did sample a whole bunch of weird people, and that's what gave us our data. And then of course, there's the other where we say, no, it didn't work when in fact it did. And there are built-in mechanisms in the statistics that we use to counteract some of these mathematically. One of them was that square root on the n that we saw way back in the z-score formula. And that takes into consideration sample size. But it also, however, it reduces type 2, but it increases type 1. Every time you have an intervention, mathematically or otherwise, to reduce one of these errors, it actually increases the likelihood of the other one. So this is the balancing act of statistics. And it goes back to that original conversation I had before about the myth that science is exact. Science measures things exactly, but it is almost always balancing between type 1 and type 2 errors. Of like, okay, did we get a false positive? Did we get a false negative here? No. And that's why replication is so important. When we go into methodology, when we go into methods next semester, I'm going to be asking you to find an article, find a study that you replicate. You're not going to come up with your own study. You're going to replicate an existing study. Now, the reason why we want to replicate studies is because of this. The reason why we write out our methods and we write out our plan and we write out, that when you're reading that research article and goes right into detail about what they did, is because the authors know that they may have committed type 1 or type 2 errors, and they want other people to be able to do exactly what they did, to do it again, and to test for those, to test to see if they got the same results. When you do that over and over and over, that's when you come up with things that are pretty solid. The kinds of things that you'll find in your introductory, the kind of things you're going to find in your textbooks about, some pretty solid evidence, stuff that's out there. It's not based on one study. It's based on hundreds of studies that have been replicated over and over. And my goal is that you would experience that, it's actually kind of tough to do. It's tough to replicate a study. even though everything's laid out, you don't have to make it up, but you have to follow their rules, you know, very, very precisely, and do it exactly as best as you can, as they did. Okay, so that type 1, type 2 is part of one of your labs. Lab 24. No. Lab 20. Lab 25 has some questions about that. And then we go into lab 27. And it's giving you all the stuff for just computing a z-test, z-scores. All pretty sure you have to do some thinking there, but you have to do your z-scores, look them up, and find out whether or not you have significant results or not. So that's what, and the discussion here is null results. Yeah, I'm sure that sort of goes into, in my own writing, I go into the importance of finding no relationship between something is sometimes really good. Like, imagine if we found out that there was no relationship between a factory closing and alcoholism. We know that there is, but if we did find out, that'd be great. That's one less thing to worry about when a factory closes. So, or if we have a really, you know, if we have a really, really expensive program that we've invested into and we find out that it doesn't make a difference, let's just shut it down and we don't have to spend all that money. How cool is that? So, all right. So I have, I'm running short on, do you have any questions about any of this?
Nope.
You're all set? Okay, so remember, you're guinea pigs for my teaching as much as guinea pigs for these tests, you know, so we'll see how well I did in presenting. And so if you have any questions, send, I know I've heard from both of you, so I know you can send me questions and ask me about stuff going on. And I'm also for, Jordan, you've registered?
No, I'm gonna do that after this.
Okay. If you could send me an email when you do, because I want to go in and I'm going to do my own check to make sure you guys are graduating. I'm sure you want to graduate.
Cool.
And I have, right now, I've opened conversations with UMA, UMO, Thomas, and Farmington. I'm currently right now emailing them to create articulation agreements, and that's the term for how we transfer credit over to these colleges. So I'm hoping to have that all done so that you can just send them your transcript and they already know where everything is going, and it kind of eases the transition into those programs. Each one is to their psych program, except for UMA, theirs is into their social sciences program. They don't have a psych program at UMA.